Good morning, everyone. This is Julie McDonald with Microcom Technologies, and I'd like to thank all of you for attending today's webinar with IgniteNet. Today's host is Dan Kazwara, and he is their field application engineer, and he'll be presenting today. If anyone has any questions, please submit them in the question box, and Dan will answer them at the end of today's presentation. Dan, thank you so much for being with us today. We greatly appreciate it. I am finished for now. Please go ahead and take it on over.
All right, thanks, Julie. Thanks for having me. And thanks to everybody who's attending today's webinar and taking time to attend my presentation. So today I'm going to talk about RF myths. I think it'd be fun to have a little twist, a little difference. Yeah, I'm going to talk about 60 gigahertz related stuff. The RF bits, most of them are related to 60 gigahertz, but it applies to RF as, in general. So let's get started. Okay, the first one is, and this is kind of a fun one, 60 gigahertz can't go through walls. Now, to be fair, in all practical purposes, it does not. But I came across this company, somebody told me about, that sells radios that are designed to go through walls on 60 gigahertz, a company called Airvine. And I'm like, is this really true? So sure enough, they do. And the technology is pretty much to sandwich two high gain radios to each other, between the wall. And I thought, well, I could try this. So I grabbed a pair of the IgniteNet ML 2.5 60 BF18s. If you're familiar with those, that's the sector 60 gigahertz base station. It can be a client, but most of the time it's used as a base station. So I got two of those, and those are 18 dB gain and 14 dBm output power on 60. And I put it between the walls of my home here and between drywall. And sure enough, there's a signal. There's about a negative 50 dBm signal, in fact, pretty strong signal. And I was able to pass over a gigabit of throughput through the walls. So you can actually do it, but the conditions have to be specifically designed to do it, really. So, in all practical purposes, I don't want to encourage thinking that 60 gigahertz goes through walls, but given the right conditions or in the design in a way that is designed to do so, it actually can. Okay, the next myth is that 60 gigahertz can only go a few feet. Now, if you're in the wireless internet service provider industry or a WISP, or you've done outdoor deployments, you're probably familiar with 60 gigahertz already and know that it can go, greater distances. But a lot of people, especially in the wireless LAN side, the indoor space, may not be familiar with much of 60 gigahertz. They may have known about it from 802.11ad, WiGig, and some home routers a few years ago had 60 gigahertz built in. They were tri-band routers, home routers, like 2.45 and 60, VR systems, etc. And those things only went a few feet, and definitely line of sight, and definitely didn't go through walls. So the misnomer is that a lot of people think that it's super short range. Well, not true. To educate the people not familiar with the wireless internet service provider industry, the companies like us, IgniteNet, have had 60 gigahertz products that do outdoor point-to-point and point-to-multipoint. Now, the way it's done to get that kind of distance, several kilometers, is by using very high gain directional antennas. And it's actually easy to do because the wavelength's so short. 60 gigahertz is millimeter wave. It's called that because the wavelength of 60 gigahertz is actually in millimeters. It's about 5 millimeters, which means the antennas are very small and or have lots of gain. The IgniteNet ML16035, the 35 meaning 35 centimeter radio, that's about a 12.5-inch dish, has 42 dB gain. So it's a lot of dB gain with not being very big. You get two of those and point them at each other, you can get several kilometers between each other. So And you can see on the bottom of the slide there, that is a screenshot of what I think is our farthest link that is a customer of ours sent it to me. I think that's the farthest IgniteNet link that I know of. It was using channel 4.5 with a half channel mode, and it was 4.7 kilometers. I don't really recommend that. You know, it's a little out of our recommended range, but anyway, just showing, yeah, you know, pretty good distance there. Other things to point out when it comes to 60 gigahertz, when it comes to point-to-point, point-to-multipoint, that is. Originally AD, it's 60 gigahertz is a technology that could actually provide real gigabit connections wirelessly. And with AD, you can do it sparingly, say point-to-multipoint with say a couple clients, but with now AY, you really can support gigabit wirelessly to each subscriber. The radios support, the AY radios support 15 clients per radio, and through adaptive TDMA, you actually really can get, you know, a gigabit to each subscriber. And that's something I don't even think you'll see even Wi-Fi 6E doing. You know, 60 gigahertz has got so much more RF bandwidth to work with. So that's that. And then also, you know, again, for people who are not totally familiar with the wireless internet service provider industry, 60 gigahertz has been a choice for them as an alternative to 70 and 80 gigahertz for two main reasons. Mainly, it's because 60 gigahertz is unlicensed, and the second reason is because the hardware costs are much lower than 70 and 80 gigahertz equipment. Okay, the next myth is that 60 gigahertz can't be used for any usable distance because of the oxygen absorption. Okay, and to be fair, there is more attenuation in 60 gigahertz than what you'd normally have with free space path loss alone. It's true. Now, how much? You can see the chart there on the bottom right. That's a peak of 16 dB per kilometer, right centered around 60 gigahertz, which is kind of between channel 1 and channel 2 there. But 16 dB is a lot, right? But it's not the end all, meaning if you have a very, very high gain antenna, in this case, my example, the IgniteNet 35 centimeter radios have 42 dB gain pointed at each other with 14 dBm of power, that even with the 16 dB of attenuation at 1 kilometer, the signal strength is still negative 53 dBm. Now, it would be 16 dB stronger, you know, admittedly, if there was no oxygen absorption, right? So it'd be negative around 30, 37 or so. But negative 53 is still a good signal, good usable signal. So it's still possible. It shortens the range considerably. And you can see there on, if you look there to the bottom left there, you know, channel 4, it's starting to get away from the peak oxygen absorption, so the signal strength is significantly better, minus 41 dBm. So, of course, if you're just doing a point-to-point link, you don't have any other channels you're using, certainly the go-to would be to use channel 4. Why not? Use the best channel for the most amount of link budget, you know, a greater signal margin to work with. It makes sense. And to point out also the link path tool, that chart, or the link budget tool you're seeing there in the slide, that is free on cloud.ignitenet.com. So you just create an account, you can go in there and you could go ahead and create, you know, and simulate and get estimated RSSI based on distance. You could also add in rain fade. So if you want to factor that in as well, which you should, best practice is to always factor in rain. So I encourage you guys to go check that out. Okay, myth 4, 60 gigahertz links are lost in the rain. So this myth that, you know, once there's any bit of tiny bit of, you know, droplets of water in the air, the signal just disappears and drops. The signal's gone. Not the case. It attenuates. It's just like kind of like the oxygen thing. It's the same thing. The thing with oxygen is predictable. It's the same, right? Where rain, it's variable. It depends on how much it's raining. Now, I used in this example 25 millimeters, an example A and B there on the list. 25 millimeters per hour of rain. 25.4 millimeters is 1 inch. So that's roughly 1 inch of rain per hour. So, and how much is an inch per hour? How much rain is that? You got rain zones and stuff. Well, I grabbed from the USGS site kind of what, it says heavy shower greater than 1 or 10 millimeters per hour, but less than 50 millimeters. So a heavy shower would be considered 1 inch of rain per hour, or 25 millimeters per hour. So looking at the, like example A at 1 kilometer, see beforehand we weren't factoring in rain, but let's now factor it in. So you got without and then with rain. So you can see channels, in my example A, channels 1, 2, and 3 wouldn't be good to use, but using channel 4, there's so much signal margin starting with negative 41 dBm that even with the rain, it's still at negative 52. So the link's still up. That's my point, is that signals still can be maintained up in rain with 60 gigahertz. The main thing is that you want to design the network where, for example, some installers want to never use the 5 gigahertz failover for whatever reason. They have 5 gigahertz interference, or they just don't want to be using 5 gigahertz. They actually disable the 5 gigahertz and have 60 gigahertz only. And it can be fine as long as you design with that in mind. In other words, you shrink in the coverage, you make everything a little bit smaller, and then you'll have so much link budget and link margin to withstand the attenuation of rain. At even shorter distances, like example B, you'll see at 500 meters, there's just so much signal to work with that and of course there's less rain because there's less, distance where, rain is additive. So 500 meters is smaller distance of amount of rain that would be in the way, if you will. So you can see at any channel it works. In example C, this is a ridiculous amount of rain. Example C is 100 millimeters of per hour. That's like considered like a torrential downpour, like a crazy amount of rain. And you can see at a short enough distance, even with ridiculous amounts of rain, the link actually could still stay up. So that's a myth too, that it can't work in the rain. Just, you really have to design with that in mind though. It does shrink everything down quite a bit. Another myth is that 60 gigahertz is dangerous. So why is it dangerous? It's kind of funny if you've been around wireless for a while. I remember, before 802.11 stuff, 2.4 and 5 gigahertz stuff, before roughly about 1999, everything we worked with was pretty much below sub 1 gigahertz. I mean, even cell phones were only like 800, 900 megahertz. Then they became 1800, 1900 megahertz. So, and then Wi-Fi became normal, and 2.4 and 5, what used to be scary frequencies, 5 gigahertz is bad for you. That even kind of went away over time. But 60 sounds scarily bad, right? But let's compare it to our light bulb we have in our home, right? That's 400,000 gigahertz or 400 terahertz, right? So, the ultra high, way higher frequency, and we're not afraid of light, light bulbs and stuff, and our, the sun and stuff like that. So it's not just frequency. So we're using comparisons to kind of put things in perspective. Another one is transmit power. 60 gigahertz radios are really low power. They're even lower power than regular Wi-Fi. Wi-Fi can be up to, the radio itself can be up to 30 dBm or 1 watt. These are, most radios, the IgniteNet radios are 14 dBm or 25 milliwatts. The Telegraph stuff's a couple dB more, but I don't really know of any 60 gigahertz radios that have more than 20 dBm or 100 milliwatts of transmit power, right? Really small, 1/10 of 1 watt. Compared to AM and FM broadcast stations that have 25 kilowatts or more. We got KFI over here in Orange County, and they're 50 kilowatts, constantly. The biggest one, the craziest one, I kind of use an example there. You'll see pictures there on the right side there. That's London. There's a TV broadcast station. I like using this example because it has an effective radiated power of 1 megawatt, so 1 million watts. So, and they've been transmitting in London City for over 50 years. And so that's an extreme example. Another one is comparison of signal strength and the inverse square law. So, even if you've worked with radio a long time, you guys, think of signal strength like negative 60 dBm. We kind of take for granted truly how small that signal is. By the way, a negative 60 signal, that's a good signal, right? That's a pretty good strong signal strength for, if we're talking about 2.4 and 5 gigahertz. Even 60 would be a usable signal. We'd want it a little bit stronger than that, but still, that's to remind you, it's 1/billionth of 1 watt, right? It's 1/billionth, 10 to the minus 9. It's crazy how small we are getting that signal and converting it into a whole lot of usable information. Such a crazy small amount of information. The thing is, the reason why it's so small, I mean, the transmitter starts at milliwatts and ends up in, nanowatts, and even smaller. It's the inverse square law. That's another thing that maybe non-radio people would not be too familiar with, but I bring that up because the signal naturally dissipates very quickly as you get further away as a square. Your distance doubles, it squares as it degrades, so it's 4 times weaker. So in other words, it degrades very quickly, even at short distances away from the point of the transmitter. So what that means is that your cell phone is likely the culprit that would expose 99.9% of the population to the most amount of RF because of sheer proximity. It's in their pocket. 1 centimeter away, a phone puts out maybe about a half a watt transmitter, exposes a person to way more RF than 99.9% of the population. That 0.1%, maybe those are tower climbers, maybe those are guys that work with radio, something like that, potentially, maybe. But so just putting things in perspective again, it's not dangerous. The other thing was they talk about 60 gigahertz because of the oxygen absorption. But again, remember, these signals are, how much is let's say 1,000th of 1 watt going to do to oxygen, right? I mean, it's just laughable. Most of the people that start talking about that kind of stuff, I don't really know any that are true electrical engineers or RF engineers that do it. It's usually very charismatic people that really have no background in RF or electrical engineering that kind of talk about that kind of stuff being dangerous. Myth 6 is higher frequencies don't travel as far as lower frequencies. Okay, this is kind of a trick one. It is false. Now, I use the extreme example of gamma rays coming from neutron stars light years away, and they come here, right? Their frequency is in 10 to the 20th hertz. It's like higher than light waves, right? They come here, right? They're higher frequency, so they carry. The main thing is it comes down to attenuation. It's actually, they don't go further. The frequency itself doesn't determine how far something goes. It really comes down to attenuation. It's true that lower frequencies are less attenuated. So here on Earth, where there are objects and obstructions that, whereas the real world, that longer wavelengths really do have the advantage of being attenuated less, so they appear as if they go further. But if all being equal with no obstructions, the frequency itself just carries on forever, either way. Okay, myth 7 is Wi-Fi 6E, 6 gigahertz, has more bandwidth than any other band. I'm gonna pick on Wi-Fi 6E. Great thing that we have now coming out, Wi-Fi 6E, 6 gigahertz, 1200 megahertz of new RF space, sub 10 gigahertz, awesome, right? It's awesome, it is. But let's put things in perspective. It's not the biggest band. A lot of people forget about our beloved 60 gigahertz band here. So I put a comparison. I said, you know what? Let's find out. Let's add up all the ISM or unlicensed frequency bands we have to work with. I'm referring to here in the US. We got 900 megahertz. We got 2.4 band. We got the 5 gigahertz band. We got the Wi-Fi 6E band, and then even 24 gigahertz. Let's add them all together. That still doesn't even add up to one 802.11 AD channel, not even one. So, and that's not even mentioning the future AY channel bonding of 4320 megahertz, 4.32 gigahertz channel. They're crazy wide channels. 802.11 AD is, 2.16 gigahertz wide channels, and there's, 4 channels, actually 6 to work with. Our IgniteNet has four future products, are out there that have, even channels 5 and 6. So you got a lot of RF bandwidth to work with in 60 gigahertz. Okay, and my last myth is myth 8, is doubling the RF bandwidth doubles your throughput. So that assumes that you have such a strong signal that if you were to double the bandwidth, that you're able to maintain full MCS rate, right? Your full MCS, like MCS 12, like you're able to maintain MCS 12 regardless. But that's not really usually how that happens, right? Usually what happens is when you narrow your RF bandwidth, you then increase your SNR, your signal noise ratio improves in theory by 3 dB, right? You narrow your channel by half, you gain 3 dB of SNR, which then translates to maybe 1 or 2 or maybe even 3 MCS rates up higher. So what happens is you usually get something in between. You don't usually lose half, but you don't gain double. You kind of get something in between because you gain maybe 1 or 2 MCS rates, which isn't fully double your throughput, but it's definitely not half. And the only time you really fully get half double is when you have a really, really strong signal and then you get the double. It may look nice, like especially for Wi-Fi, when you connect let's say your laptop and you see that PHY rate connection speed, really, really high number, that might look nice, but what's the actual throughput, right? And what is your backhaul or your ISP? May not even matter. You may not even notice it. For example, if you have an ISP providing 100 megs and you have a home Wi-Fi and you're using an 80 megahertz wide channel, if you were to change it down to a 40 megahertz wide channel, you're not going to notice anything because your ISP is your bottleneck at 100 megs. So, things like that. But then you figure if you go to 40 megahertz, you may find yourself having a lot more freed up channels to work with, and you may not have interference if you have more stable network. And maybe that's actually better. So just things to consider. And there on the bottom there, I'm talking about the AD. So familiar, the IgniteNet Peraso chipset on the IgniteNet Metrolink product line has the option for half channel mode. So that gives a plus 3 dB of SNR. Now, interesting to say, a lot of people, use the PHY rate. Look at the PHY rate of MCS 12 with 8211 AD. It's 4.62 gigabits or 4,620 megabits. So even if you were to go into half channel mode, it'd drop it down to 2,310 megabits. A lot of times, many installers are using the 1 gig Ethernet. So in other words, your bottleneck is your Ethernet anyways. So if you were to go to half channel mode, you may not even notice any difference because typically you'll see about 50 to 60% of your PHY rate is your actual throughput, so you'll still get you'll say your gigabit. You might as well run half channel mode. I've seen many times where people go into half channel mode and they notice no difference in their throughput because there's so much extra overhead from the PHY rate being so high. So, and the other thing to consider, channel bonding. So with AY, there's going to be channel bonding. The Telegraph product, it is in the roadmap to have channel bonding. It's basically just bonding like channels 1 and 2 together, or channels 3 and 4 or whatever. 4,320 megahertz. It's going to be huge, right? The PHY rate will go up to like 9.2. It'll be super high. The actual throughput, though, for the Telegraph, instead of being around 3.6 gigabits, is going to be about 5.5. It's not going to be double. The forwarding rate, the radio itself, is going to be kind of limited at that point, and then so you won't see double, but you will see a significant increase. But keep in mind, when you double your RF bandwidth, you lose 3 dB of SNR. So then, that's a trade-off. So if you happen to lose a couple MCSs, it may not even matter or help. So that channel bonding mode, it's probably looks more good on paper than it may be good in reality. We'll have to see how it does in the field when it's out. All right, that concludes my presentation. I'll pass it back over to you, Julie, to see if there's any questions.
Thank you so much, Dan, for that wonderful presentation. And yes, we've got some questions for you. Let's get started with the first one. Let's see. Will your devices support 60 gigahertz in the near future?
They do. There's two, okay, just to clarify. So EdgeCore makes a 60 gigahertz product called the Teragraph. It's you could look it up. It's the MLTG Teragraph product line. That's 60 gigahertz. EdgeCore also owns IgniteNet. IgniteNet's been around for many years. Some people may be more familiar with IgniteNet as a 60 gigahertz solution. EdgeCore and IgniteNet are really the same company. EdgeCore, is part of IgniteNet. So yes, we do, and yes, we do is the answer.
Fantastic. Thank you, Dan. Can you tell us about the warranties on the devices?
Yes, I believe, now I'm going off memory here, the Teragraph stuff has a 3-year warranty, and I believe the IgniteNet has 2 years.
Okay, fantastic. Thank you so much. Next question here for you. When you talked about penetrating walls, can you tell us a little bit about what materials it can penetrate?
Okay, well, again, that was really just for kind of busting a myth that, given that, I wouldn't recommend it, but yeah, that's not something I'd say our product lines really do. That's something that's another company specializes in that does that kind of stuff. They even have a little chart showing attenuation at 60 gigahertz, like through certain like concrete and stuff like that. So I'd say check them out. It's not something we do. It's just I just wanted to point that out. Can you use our product to do it? Yeah, you can. I mean, I did it through drywall. I would think it would work through wood sparingly. I mean, like the side of a building, probably. I mean, you could try it, but I mean, it's not something I'm going to recommend or anything. Our products weren't really designed to do that. It was more just for kind of having a fun thing with myths about, that 60 can never work through a wall. It can, but I haven't done any actual testing to really know how well it can do it. I mean, if you already have our product on hand, you could certainly do it for fun and try it out, but I wouldn't say I can't really say endorse doing it so much.
Okay, thank you so much for that, Dan. Next question here for you. Regarding maximum distance, what information do you have available to give us an overview on that?
Well, yeah, you can check out the data sheet, say on the IgniteNet stuff. The data sheet will say that we recommend up to 1.6 kilometers or 1 mile for point to point. I mentioned that 35 centimeter model. That's the higher gain or the highest gain radio that has the most dB gain. They point them at each other. So that specs out at 1.6 kilometers or 1 mile for point to point. For point to multi-point, we recommend up to 500 meters using a base station, which has lower gain, with a higher gain directional pointed back at the base station. Up to 500 meters is what we recommend. Now, do people go further? They can. They have, and with the 5 gigahertz failover, you could be a little more risky if you want to be, or if like that one customer, he got a 4.7 kilometer link. That's like the farthest link we've ever seen, though. So realistically, I've seen it's common to have customers do 2 kilometer point to points. But past that, I would say probably look at some other things to go further than that. There are some other technologies that do it, but we have other advantages in the fact that we have our I would say our cloud. If you haven't used our cloud and the management of the product is in my opinion, one of the best in the industry. It's one of the easiest to use, simple. Like I said, it also has the EC cloud, the IgniteNet cloud. Has the 60 gigahertz, the tool to give you your link budget, but it's super easy to use. It's also, you don't have to go, I know some say the manufacturers have those tools, but they're always hard to use, and it takes there's like a learning curve, you know. This stuff you just go in there and click this and click that, and you already got your an RSSI estimation. It doesn't require a whole technical amount of knowledge to get somewhere with it, which I think is really good.
Excellent. Thank you, Dan, for that. Next question here for you. Will all of your devices support Wi-Fi 6 in the near future?
Okay, so Wi-Fi 6. So currently EdgeCore has indoor APs and indoor and outdoor APs. You know, the models that you want to check out are the EAP 101, EAP 102. Those are a 2x2 or a 4x4 Wi-Fi 6. Now, not to be confused with Wi-Fi 6E. This is Wi-Fi 6, meaning 802.11ax. Now, if the question was 6E, meaning 6 gigahertz products, that's slated for the future. We don't have any currently yet Wi-Fi 6E or 6 gigahertz products yet.
Thank you for that, Dan. Thank you. Next question here. Will your link devices include all mounting point parts?
Yeah, it depends on the model you're getting. The Metrolink products, you need to buy a separate mounting bracket. With the exception of the omnidirectional base station, all the others require a separate mounting bracket. That's for the Metrolink product line. Now the Terragraph EdgeCore product line, the client nodes, they don't require a mounting bracket, and the distribution node doesn't either. So in other words, they aren't needed for either. They're included. So it just depends. The only exception is the CN, the client node long range, or LR, that we're going to be coming out with very shortly here, that has that you would need a mounting. But the mounting's the same as the Metrolink. It's basically the same thing as like it even looks similar to the ML16035. So it'll have the same mounting bracket in the back. It'll have the alignment scope mount, just like the IgniteNet Metrolink 35 does. So you can check that out, the CNLR. So hopefully that answers the question. Back to the mounting brackets, like I said, all the Metrolink radios require purchase separately, except for the Omni. And then for the Terragraph products, the CN and DN include a mounting bracket, and the CNLR does not.
Very good. Thank you so much, Dan. Last question for you. Can we go to your website, and if so, just tell us exactly where to go, where we can find all the general information like customer service, and especially tech support. Can you guide us there?
Yeah, well, okay, so you could go to support@ignitenet.com or support@edge-core.com, either one. You'll see on the slide right here, it says sales@edge-core.com. You could do the same to go to sales@ignitenet.com. They just go to the same group now. So either one, that would be your best bet. I suggest emailing is probably the best way to reach, for like the best way to start initial, for support. Now the websites are www.edge-core.com and then or www.ignitenet.com.
Excellent, Dan. Thank you so much for answering all of those questions for us today. And thank you to everyone for attending this webinar. And if you have any further questions, please feel free to contact your sales rep or email us at sales@microcomtech.com. And if you wish to view the products mentioned or shown here today, please visit us at www.microcom.us. And please remember, this webinar presentation has been recorded and will be uploaded to our Microcom YouTube channel so you can view it again. Dan, thank you so much for being with us and sharing all of this wonderful information. We greatly appreciate it. Everybody have a fantastic day.